Hi, welcome to our presentation on the Fatigue Lab. I'm Eric Markham.
I'm Connor Witten.
I'm Stephen Hanada.
For this lab, we were given a 60 by 61 aluminum rod to which to test fatigue. We were given two stresses to test for, the 40,000 psi and the 25,000 psi. We happen to use the 25,000 psi just for simplicity's sake. When we set the aluminum rod into the tester, it becomes something like a cantilever beam, as shown in this diagram. For simplicity's sake, we wanted to test our load at 12.5 inches away from the clamp. We also needed to consider the stress concentration that is caused by the groove that is cut out of one end, along with how much load that we can put into to make sure that this thing fails.
This photo is a photo of the sample after it has broken in the fatigue tester. We have pulled out a little piece of sample from the chuck to show that it has broken on the stress concentration line, which was just a little groove dug into the side of the sample.
It's worth noting that the bearing has its own weight included with the weight that we're going to apply, so we made sure to calculate that into our equation. So this is just to show what we did. This is not the actual full length of the bar. This is after we tested it, but I wanted to show you all how I set it up. We put the bar into the chuck, tighten it up, and then we have the bearing and the load, which you apply at the end. We were given rods that were a bit too thick, so we actually had to sand it down into more of kind of a point to fit it in. Once you have that done, you go over here and hit this power button, and you let it test until failure.
So for this lab, we were given an aluminum beam. This has some stress concentrations built into it. So we needed to determine the stress concentration factors so we could find out what stress we would actually need to use for our other calculations. So when we went and asked Paul, our lab manager, what the dimensions of the groove he set into this aluminum bar were, he gave us that it was
20 thousandths of an inch deep, 20 thousandths inch radius.
So from these, we were able to determine our KT factor. That we determined from looking in the back of the book and comparing the ratios. So using that, we were able to find our stress, the actual stress that we were able to use in our other calculations by dividing the maximum stress that we could apply to find our nominal stress by dividing the KT factor. So here we found that the stress we would be using for all of our calculations was 11,520.73 psi.
Our stress equals MC over I, but we knew our ending stress is what we wanted as we calculated from our stress concentration value, but we did not know where to put it at along the other rod, and we didn't know how much weight to put on there, so we had to solve for that. We ended up taking length as a constant, which made our calculations easier, meaning we only had one variable to solve for. Our constant was L, which is 12.5 inches along the length of the beam. So using algebra, we're able to transform M, which was our moment caused by the length times our load, equals I, stress times I over C, which we're able from there to transform that into our point load equals stress I over length times C, which equals, this equating comes to roughly 5 pounds. This is it rounded down to make it a more digestible number. It's like 5.00. And this weight, we know the bearing on the actual fatigue tester would have a little bit of weight on the point itself, which we measured as 2.15 pounds. So we're able to subtract 2.15 pounds from 5 pounds, helping us find the actual value that we needed to place onto the actual fatigue tester. With that, we were able to get a total of 7,618 revolutions with that 5 total pounds of weight upon the weight of the bar at 12.5 inches.
Please direct any questions regarding this lab to the email of Connor Witten, Eric Markham, or Stephen Honadell.